And hello, welcome back. So in the last video, welcome back to our video series on turbulence modeling. In our last video, we're talking about the smooth function. The smooth part where, if you take a look at the later lines, being about 179 onwards, this is the smooth function, and the code actually tells us what formula are being used. And in over here, we want now that we understand the smooth function, we want to look at the rough function as well. So we want to compare what we know to what OpenFoam uses. So this is from line 115 onwards. So let's take a look at what we know. This is what we are familiar with. Okay, and what we are familiar with is this kind of function: u plus equals 1 over kappa ln y plus c minus delta u. Okay. Yeah, so what OpenFoam uses is the exponential form. It combines this c, okay, for smooth walls. Okay, it combines this c into the equation here, u plus equals 1 over kappa ln y plus into some value e. So this e is, you just combine this c into this ln term here, then you have e equals to 9.8, kappa equals 0.41, and c equals to 5.56. All right, this is what we were dealing with the last time. So now for rough walls, u plus equals to 1 over kappa ln e y plus. Okay, so we know that these two expressions are pretty much identical mathematically. So now we have this delta u plus at the back. Okay, we have this delta u plus at the back, and if you recall, I just copy and pasted this whole thing here. If you recall, the delta u plus equals to 1 over kappa, which is 1 over 0.41. Okay, kappa. And this is also kappa here. So the expression here is 1 over kappa into ln hs plus, this is the dimensionless roughness height, over exponential 3.25 times kappa. Okay, so this is for the rough walls. So now we will try to decipher what OpenFoam uses. Okay, so from the source code. Okay, so from the source code we can see from line 115 onwards, they use the same smooth wall function definitions. However, there is this dks plus dy plus. So let's write that down. Okay, so we have dk s plus dy plus, oopsie, y plus. All right, so this is this one over here. All right, and we'll have a roughness height over the y. Okay, so that's just roughness height hs over y, or if not, var epsilon divided by y, and this is the same as saying epsilon plus divided by y plus. That means you just normalize the top and the bottom by the same factor, the friction velocity and y, you will get this formula. So no problem. So this is dks plus dy plus. Okay, that is one. Then you'll have this one, additional tuning factor, where we have this roughness factor over here, which you can define yourself. Okay, so dks plus dy plus equals to times equal roughness factor. What is this times equal roughness factor? This is a very shorthand for in C++ code. All right, so in C++ code, let's say A equals to times plus B, okay, or okay, times equal b. When we write this, this means, if I'm not wrong, a equals to a times b, or a is defined as the new value of a is defined as the old value of a times b. So what this is saying, so we have dks plus dy plus equals to hs divided by all. We use var epsilon because that's what we see in the Moody chart often, divided by y times a constant, some constant, k roughness. Okay, what is this roughness constant? Well, or roughness factor. So I'll just put f roughness instead. So roughness factor here, the roughness factor here just gives you the freedom, okay? It just gives you the freedom to add a constant in front of this epsilon over y, or the roughness height over y. So this just gives you the freedom to do so. The default value, okay, you can just put 1 there. All right, see, roughness factor, this one is a typical value, okay, which is 1. Okay, so we'll put it here. By default, f roughness equals 1. So that is that. And of course, at this point, we don't see a delta u plus equals to all of this yet, but let's see whether we can get to something similar like this shortly. Or at least when we plot this out on the graph of delta u plus against hs plus, we can see some resemblance. Hopefully that's of course the intended outcome, right? So let's see what we can do next. Okay. So we have this dks plus dy plus equals the epsilon over y times some roughness factor. So we see this ks plus, okay? We have this non-dimensional roughness height equals to y plus times dks plus dy plus. So okay, so we have ks plus equals to y plus times dks plus dy plus equals to y plus times the whole lot over here. That is what the code is saying. Alright, this is at line 134. Okay, so that's all the code is saying. I can take away the times just to make it more compact. Alright, so that's ks plus. Then we have some g over here, which we just ignore. So now we have this ks plus, okay, ks plus equals to 90 or greater or equals to 90. So what is ks plus again? Okay, if we take a look at this ks plus equals to some constant f roughness. Okay, so typically that's equals to 1. So y plus will be multiplied into var epsilon plus over y plus, because again we can divide both bottom and top by the same scaling factor, and then what we can do is just have this final form. So I'll just copy this and paste this here. Okay, otherwise if you are more familiar with the hs plus term, it's also equals to hs plus. So hopefully we see that, okay, this is actually the same. This is what ks plus is talking about. Okay, so for ks plus we have a few regimes. One is where ks plus is bigger than 90. So first regime, okay, ks plus more than 90. This is from line 141. 141. Okay, so ks plus bigger than 90. So we will have a constant scalar t1 equals to, alright, let's just write this down first. T1 equals to roughness constant times k plus, or 1 plus roughness constant times k plus. Okay, so 1 plus so this is a roughness constant, right? Roughness constant is k roughness. I'll just call it k roughness times ks plus. So ks plus. All right. What is the value of this roughness constant? Now this is something you can adjust. You can also adjust k roughness but default value is 0.5. Okay, so if you take a look at the entries here, I mean this is the boundary condition specification. We have roughness height as some this one you have to specify in meters. So this is 0.1 times 10 to the minus 2 millimeters, or 1 times 10 to the minus 5 meters, or 10 micrometers. Okay, roughness constant is 0.5 by default. Roughness factor is 1 by default. These are some suggested entries. So but of course we can adjust till we get this what do you call that, we get this value. Okay, so that is what we want. So we can adjust k roughness as well, but we tend to like to leave it at 0.5. Okay, so this is T1. This is T1. So G equals to logarithm of T1. Okay, great. So so OpenFoam tells us, okay, I want to define this term G. So let's just say G equals to ln of T1. So ln of this whole thing here. Ln of this whole thing here. And y plus G prime equals to roughness constant and ks plus over T1. Okay, we'll just write that down. Y plus G prime equals to this whole thing here. Okay, roughness constant times ks plus. Alright, and then you divide it by T1. So this is T1, we divide it by that. So I don't know what this is yet, but we'll find out shortly, hopefully. Roughness constant times ks plus. Roughness constant times ks plus. Okay, there we go. Yeah, so we don't know what this G prime is yet, so we have to dig into the code. Okay, what relevance are G and G prime? I don't know yet. Let's keep looking. Alright, so this is for ks plus more than 90. Alright, so this is the second regime, ks plus less than 90 but more than 225. Okay, so if the roughness constant is more than 2.25, second regime, ks plus, well, we already tested that is less than 90, but it has to be more than 2.5 or 2.25. Right, 2.25. Okay, so this is what the code is saying. Else if blah blah blah, then if it's less than 2.25, we will adopt the smooth function. Remember, I was talking about if, okay, third regime. Less than 2.25, smooth wall. Okay. Okay, so this is the third regime. So I'm just explaining to you what the code does. This plot is okay from KS plus from 2.25 all the way up to 90. Otherwise, we'll just use the smooth regime. Okay. Okay, so this is the other parts of the code which I'm going to just ignore. Yep. So anyway, so this one is the KS plus more than equals to 90. This one is less than 90, more than 2.25. So it defines a scalar denominator here. Okay, so I'm going to skip the second regime first. I'm going to go tell what this denominator thing is. So let's write the denom. Okay, so this is the first regime, second regime. Okay, OpenFoam defines a denominator. Okay, so the denominator is this denom equals to, so this is from 158 all the way to, okay, this is just 158, right? Line 158. Line 158 of that roughness function. So equals to 1.0 plus log e into yp minus g minus y plus g prime. So let's write that down. 1.0 plus log of e into yp. So log e into y plus, or ey plus, close bracket, and then I will have a, so yeah, so let's just write that first. That's the denominator, minus g minus y plus g prime. So y plus g prime is here. Looks like a very complex model. So this is a denominator, and then it says if the magnitude of this denominator is more than v small. Okay, so I guess this is just some test factor. Okay, I'm not going to bother what that is, but if this condition is satisfied, then we will have this y plus over here equals kappa Reynolds number, okay, plus y plus times all of this. Okay, so let me write that down. At line 161, we'll have a y plus equals to kappa Reynolds number, kappa Re, plus y plus times 1 minus the g prime thingy. Okay, so 1 minus the g prime thingy, 1 minus the y plus g prime. Okay, so it looks really complicated now. Ooh. Okay, and the whole thing is to be divided by this denominator. The whole thing is supposed to be divided by this denominator. Okay, so that's quite a mouthful again, as usual. All right. So let's see. Let's break it down. So this form, this highlighted form here, this is actually what OpenFoam uses. Okay, so I'll stop the video here, and in the next video I'm going to discuss more how we can manipulate this to fit a form that we are familiar with, i.e. to say this form. So this form. Okay, so thanks for watching. I'll see you guys again. Bye bye.